Uh, uh, Hi. Hi, everyone. Hi, hi, everyone. Are we ready? Woo! Hi, everyone. Thanks for being here for the second week of member series this year. Today, we have Pedro as a speaker. Pedro is a second-year grad student studying physics at UBC. He also studied physics for his undergrad in University of Granada in Spain. So as you can see, he is a very physics enthusiast, and anyone who knows Pedro well, he's a very working so hard. No matter how early or how late it is, you'll see him working at his desk. When you pass by his door or window. So I think, we are lucky to have Pedro as a speaker for explaining us about the history of universe. So let's have for start.
Thank you. Okay, well, is this on? Yeah. Oh, sorry. Well, thank you everyone for being here. First of all, I would like to begin by acknowledging that the lands on which we gather today are the ancestral and ceded and traditional territories of the Maskian people, and that we are thankful for being able to work and live here. Well, as Junsiab said, I'm Pedro Villalba González. My pronouns are he, him, his, and I'm a second-year grad student here at the Department of Physics and Astronomy, where I work in observational cosmology, which is closely related to this. And we are right now building a radio telescope which will help us look for this radiation from the very early universe. Before that, I want to talk a bit about myself, even though Junse gave a perfect introduction. This is a picture of me with my parents in Spain, as he said. I'm from the south of Spain, from a small town called Granada, and this is one of the stunning views that we have from there. And if not, you can also ask Sancho, who is also from there, about how nice our city is. And okay, well, today I'm going to talk about the baby picture of the universe, how I and other cosmologists like to call it, which is the cosmic microwave background, which is this light that is present in the whole universe and that was emitted when the universe was only 300,000 years old. The universe is right now 14 billion years old. So if we compare the universe to an human to an 80 years old human, it's as if we took a picture of the universe when it was only a couple hours born. So we can get a lot of information of how the universe evolved from there and how the universe initially began. I structured the talk in the following way, and it's a bit of an experiment, which I'll see if it works or not today, so bear with me. I'm going to start by introducing some of the tools that we have to understand the universe and how, through history, different civilizations around the world have engaged with the sky in a way of explaining why they were on Earth. Then I'm going to give a very brief history of the universe, and then jump into the cosmic microwave background. And in order to talk about the cosmic microwave background, and this is where I'm going to do the experiment, as I'm an observational cosmologist, I'm going to talk about how we can obtain information from this CMB, or cosmic microwave background, following the history of the experiments that have enabled us to measure it. And after that, I'll briefly talk about what my part in this research is and how the research is going to look like in the next 10 to 20 years. But before that, I'm making my undergrad thesis supervisor words mine. I just want to say that there are no stupid questions, there are only stupid answers, and for some reason people are really afraid of asking things about science. Please ask me anything and please interrupt me through the talk. Don't wait until the end. If I don't have enough time to cover the full talk, that's fine, but I'd rather have this kind of, not dialogue, but if something that I say is not clear, you couldn't understand what I say, just interrupt, just raise your hand and I'll clarify it. Okay, so Cosmology, or basically the science that wants to explain why we are where we are and how the universe evolved up to the position where it is, nowadays is as old as humankind is. Since the human is human, we've tried to understand why we were here, and there are archaeological rests from like 30,000 years ago that already show how like humans will try to seek for this kind of explanations. The way that civilizations have done this through history has been by looking at the sky, and every civilization has had its own way of looking at the sky, upon engaging with this kind of observations. But it was not until the 17th century when we were able to look at the sky with something else than our naked eye. It was Galileo, even though it was not his original invention, Galileo Galilei was one of the first person and the one that basically opened up an era in astronomy by pointing a telescope at the sky and discovering some of the, what we know now today as the Jupiter moons and some other celestial bodies. From here, people began building bigger telescopes, began making them more powerful and making it easier to gather information from them. And nowadays, we still do it. We have the Very Large Telescope. This is the name that it has, the VLT, which is a huge telescope in Atacama, in the desert of Atacama in Chile, at like something like 600,000 meters. And we still make use of this kind of observation. Up to now, I've been just saying on how like we look with something similar to our eyes, or something where we will put our eyes and basically the image will be magnified and we will see objects farther away. But there is another window or another frequency, and this word will make sense a bit later in the slide, that which we can look at the universe, and this is radio waves. These are the same radio waves with which we can basically like turn on a radio and listen to the CBC News or listen to some Shakira songs. And it was not until 1931 that a scientist called Karl Jansky in the Bell Laboratories pointed his antenna to the sky and realized that our galaxy actually emits radio waves. What I'm showing here on the right is a map of the sky projected in such a way that this line is the galaxy. So basically, we know that if we look at the sky nowadays, today, and the sky was clear enough, we will see how the galaxy did this kind of thing. What we've done in this transformation is to just put the galaxy here. We've done this just by convention, by how astronomers like to label points on the sky. But what is a radio wave? A radio wave is not anything else than a specific kind of electro. Yes, Merlin?
Question to the slide before.
Yeah.
Why is it round, the right picture? Why is it so other?
This is called a mold-wide projection, and it's a way of projecting a sphere into a plane. When you have something that is spherical, as you could imagine the sky has been just like this sphere that covers the full Earth. One of the ways that we have to show it is by doing this kind of projection.
Why isn't the image spherical? Or why was the object spherical?
Because the sky, like imagine the Earth. If you like, let's say that you have the Earth, like you take it as round, like a sphere. If you look at points in all directions, that's basically a sphere.
Inverse.
Yeah. It's like projecting the image of the sky into Earth. That's what it's being done here. Okay, so what is radio waves? And this is what I'm going to be talking for the rest of the talk. A radio wave is not any other thing than a special kind of electromagnetic wave. We are, I will say, not nicely used to talking about light as just this visible thing that basically that light bulb emits or light that gets to us from the sun. Light, or visible light, which is here, is just has a specific size that makes it different from the rest of the spectrum. from the rest of the radio, microwave, infrared, and has an associated wavelength to it. This is what makes, if I imagine a wave has this sign, has this periodic movement, the distance between 2 points which look the same, in the case of visible light, is very small. It's something like 0.5 times 10 to the minus 6 meters, which is, has here a protozoa size. But when we go to radio waves and microwaves, we have larger waves. When we go to radio waves, we have waves in the order of 10 meters, 100 meters, 1,000 meters, and microwaves are 10 to the minus 2, which is 0.01 meters. And these are the exact microwaves that are in our microwaves, even though I have to make the joke now that Mark is here after the dinner. But apart from this, it also opens up a whole new window to the universe. And it's the fact that if we look at the sky with, in this range, if we look at the electromagnetic waves that are traveling through the sky, we will see that if we remove the galactic contribution and we remove any other contribution from any known sources, we get an uniform radiation with small differences which are shown in this map. Remark that the differences in this plot are of the order of 10 to the minus 5, which is, they are uniform in almost a part in a million.
What do you mean by saying remove any galactic contribution?
The same way that you have, look, this picture is taking a frequency of 100 gigahertz, which is something like a wave of 3 centimeters, more or less. This picture is taken at 408 megahertz, which is something a bit larger. If I go down in frequency, I would still have a map like this, but it will look in a different way. But that radiation comes from the galaxy. The same way we have other extragalactic objects, which are, for example, like there are some galaxies that are far away from us that also emit radio waves, but we know them. So if you take a map of radio waves and you remove those contributions, you have this remnant uniform radiation that is the cosmic microwave background. For example, if we look at this, I think this was a nebula, I don't exactly remember the name, but if we look at it with in the optical range, we have this image. And then if we look at it with radio waves, we have this other image. So for answering your question, what we will do is, okay, we know that this radio emission comes from this nebula, we just remove it from the map. And even though all this might sound like a bit esoterical, what I've been doing up to here, there is the science behind this is the same science that in the infrared cameras that we have. And the nice thing about this kind of, this is called multi-messenger astronomy, is that we can obtain different information from looking at it. So if we look at this person picture, we could get information on some of the distinct colors of the hair, of the t-shirts and all that. But we couldn't get any information of its temperature just by looking at these two drinks. We don't know whether it's hot, it's warm. But if we look in the infrared, has hot things emit in a different frequency that cold things, we have this distinction. And this is exactly what astronomy do, and this is another whole window of observational astronomy, which is, as I said, multi-messenger astronomy. And one of the remarks and maybe shocking things about these electromagnetic waves is that they all travel at the same speed, and this is the speed of light. But the speed of light doesn't mean that only visible light travels at this speed. Radio waves travel at this speed, gamma rays, infrared, all the full spectrum travel at it. And this has I don't know if I would call it philosophical, but deeper significance, and it's the fact that we are always looking into the past. So to understand the present, we need to look at the past. Same thing that when we look out in the universe, we are looking at the past. Just by the distance that we have, for example, from here to the sun, the light from the sun takes 8 minutes to reach us. But if we look at the center of our galaxy, that light takes 28,000 years to reach us. So let's imagine that we had a telescope in the center of the galaxy, and we could resolve an image on Earth. For that, none of us, for an observer in the center of the galaxy, none of us would be here, and there will be basically the world wouldn't be the same place that we know it to be nowadays. And this makes it, even though it might be a bit sad that we cannot get information from how the universe looks right now, give us information, give us a window of understanding the past, the history of the universe. And it's just, if we look at things that are farther away from us, we will be looking at more and more past. So if we start by looking at closer things, we have, first of all, the solar system. These things are just like minutes or hours away from us at the speed of light. But then we have closer stars. For example, we have Alpha Centauri, these other stars here. And we also have our galaxy. And we have other galaxies. And if we keep on going down and down for almost the 14 billion years that the universe has been born, we can look at some of the first stars that were formed and some of the things that were here, which were not even stars or galaxies, that was just dust trying to form these stars when the universe was only some 100 million years old. There are telescopes such as the James Webb Telescope that can actually look into this area, which is fascinating me. Yeah.
Sorry, just to clarify, what is the images that we're seeing here?
Here?
Like just in general, I'm kind of getting confused, like
Yeah.
what are the actual images represent?
Wait, these ones? You mean in this plot?
Yeah.
Okay, this is a represent. When galaxies form, they try to come together in something that is called the cosmic web. So in this picture, the way that I will think about this is has each of the dots is a galaxy.
Okay.
And you can see some of the cosmic structure here and how in parts where these parts are called voids, which the universe is full of this, there is like nothing other than, like there is basically nothing because of the gravitational attraction they tend to cluster together. So if we keep on looking far, like deeper and deeper, there is a point, which is when the universe was between 300 and 400,000 years old, that we get to this uniform radiation all over the. Yes.
How can we resolve the contradiction that we, on the one hand, want to look further and further and further away, and then on the other hand, we have only a small point and the beginning? That means somewhere there is further away, and where are we? Are we in the center? We don't know, right, where we are. This somehow means.
If I knew how to answer this question, I would get a Nobel Prize. Because that's the way that we think. And let me wait 2 slides, and if not, I ask again, because that's exactly the information that the CMB tell us. So, as I said, we are going to look at this map. This is the same map that I showed before, and turns out that this radiation is uniform and gives the universe a temperature of 2.75 Kelvin, which is minus 270 Celsius, a bit colder than Vancouver in the winter, but not too much. And in order to understand this radiation, I've been looking at the universe, at the history of the universe from the end to this midpoint, which is called, just for the sake of saying the name, recombination. I've been looking at from our days to this recombination age. Now I'm going to look at the history of the universe from the beginning, or almost from the beginning, to when this cosmic microwave background was formed. Even though I would love to talk about T0 of the universe, I'm only going to center myself into a time of 10 to the minus 34 seconds, which is 0.0 with 34 seconds behind it. What happened before, and I think that relates to your question, Merlin, is not clear. It's not clear that we could use the physics that we have nowadays, because we have some scales which are called the Planck scales, in which basically the way that we understand quantum field theory today breaks down. So we don't know if we could. If you think about it, the way that we do physics is we do some observations on Earth, and some observations with telescopes and all that. But we assume that the same laws of physics that we derive for us, we assume that they work in the past. But there is really not too much evidence that that's the case. So for example, there are like some principles that we take as true, that some of them has proven to work in other scales that we haven't tested them, but we are not sure if this is the case. Anyhow, I'm going to take an educated guess, and yes.
Yeah, so there's this thing called Doppler shift, right?
Yes.
Which is like the things are moving far away from each other. So if we work backwards, can there be some explanation that it was singularity at some point and where that point was? Is there some kind of new findings in this?
Again, I will get a Nobel Prize if I knew how to answer this. I've tried to skip the redshift. Actually, the way that I know that we know the age of the things is by looking at the redshift and just looking at how redshift is. If I have a wave coming to me and I'm moving away from it, the frequency that I perceive is not the same frequency with which it was emitted, basically because the wave is like, we see the wave has been larger or has been smaller. So the farther we are, the more redshifted the way it is, and it's called redshifted because it goes to the red part of the spectrum. And I think what you were asking is if like we can trace them, we will be able to get to the singularity. We don't really know what happened. We don't know what happened. What I'm going to talk about, we are not sure about it, and you can see some like really famous and good cosmologists debating options. We don't really know what happened. We don't have a solid. I would say we don't have a more solid theory than this one to explain what we have. So.
Maybe you're the one to discover you.
I would love that. If I get tenure at a university, I'm happy with that. I don't need the other.
But you might come across it accidentally, that's how our theories are coming up.
I would love that. I would love to do that. So if we now look at this at the universe when it was only this young, what we think that happened is that it expanded exponentially really fast in something like less than a tiny fraction of a second. It expanded in a factor of 10 to the 20, 10 to the 24. And initially it was really, really hot and really dense. With this expansion, it cooled down a bit, and there were some tiny fluctuations from this initial density that are the seeds that we see in the cosmic microwave background. So to put it another way, before, let's say, an instant before this happened, we had a very hot thing, like a very hot small thing. It expands exponentially, and even though in principle these conditions are random, this is like we just think that the initial density is like a random thing. At the moment they expand, they become more uniform, but still not uniform at all.
That expansion happened at a faster rate than the speed of light.
Oof. Faster rate of the speed of light, yes, and it doesn't break causality, if that's what you are asking. Causality is this thing that that basically things have to happen before the other thing. So if I have something traveling faster than the speed of light, that means that I can like break an egg before cooking it, because if you send me a light signal telling me to break the egg before I break it, yes, and that's something that it does. The theories that we have right now, it's that expansion happens, but it happens in a way that it's the space itself what is expanding faster, not the things on the space. Does that help? Okay. I like to think of this as if I had a globe and I put air into the balloon. The space is going fast, but the things moving inside the balloon are not. Don't quote this in front of any theoretical physicist, by the way. Okay, so after this expansion has finished and we had these initial seeds, our universe is still super hot and super dense. Then we have no distinction between photons, which are these light waves, electrons, quarks, which are the constituents of matter. So everything is forming this quark-gluon plasma. As the universe, has time passes and the universe cools down, the temperature start becoming smaller, and it starts particles start colliding less and less and less at a smaller rate, and there is a point in which is at this recombination age, which is when the cosmic microwave background is emitted, in which the photons last collide with the particles that are free at this point, and they emit this light, this afterglow of creation that is the cosmic microwave background. Yes.
There's a lot of questions, maybe I could say this earlier, but I'm curious if you could explain maybe a little bit more what you mean by temperature. When you're talking about a soup of things that are smaller than atoms and smaller than sometimes the things that make up the atoms. Are you just talking about kinetic energy? Are you talking about some sort of like other sort of energy? Things have, how are you conceptualizing?
This answer is not 100% rigorous, but you can think of it as a rate at which particles are vibrating. You can think of it as that.
I'm just curious because, like, from a physical chemistry perspective, like, you can reduce a lot of things. You can reduce the definition of temperature to mostly just kinetic energy. So I'm curious, like, that far back, how far that definition holds up or not, because most physical chemists don't spend much time thinking about cosmology.
You can think of it as an statistical mechanics point of view, as you were saying. Yeah, has the
I have a question. How come there are some areas that are over dense and under dense?
Very good question. Very, very good question. This that's another way of using the cosmological parameters, cosmological parameters, but those are much, those are like more, these are more direct measurement, but for example, we are not sure if the model that we use to measure these diamonds is good enough or not. And the cosmological background is just, is something that we measure that way, and that just happens to be there, but it's
Hi. So my question is, with like radio, so maybe I'm just not quite understanding this part, but with like the spectrum of light then, and in exploring the different parts of it and moving beyond visible light, is it that like in looking at smaller waves, we're able to kind of answer further questions about the nature of like what the universe started as and looked like, or? And then I guess like kind of following up, like do people read the way the universe looks in relation, like from looking at radio waves and looking at microwaves and infrared waves, like in any kind of collective way? And what does that tell you differently?
the cosmic microwave background, it happens to be nature has been nice enough for us, and it happens to be there. I'm saying nice because if it was in gamma rays, our atmosphere prevents us from looking at from getting gamma rays, which is good for our health, but wouldn't allow us to look there. Like the way that astronomers, when they look at the universe, look at it is by using the full range. So you will have the way that this will be done is, for example, for some, if you want to see whether something very far away is a galaxy or not a galaxy. And apologies, there is a galaxy number here because I'm waiting. But you will look, for example, you will have infrared measurements or visible measurements, and then you will correlate those measurements with other frequencies, for example, many radio waves, but I wouldn't. Radio waves mainly come from our own galaxy, and when we look at our own galaxy as well, we will look at radio waves in our spectrum. We will look at maybe like some frequencies, 100 megahertz to hundreds of gigahertz, and we will obtain other information from them. I have a picture here. This is the same, this is our galaxy. Look at the different frequencies. You see all how different the frequencies can obtain. This is how the people do astronomy.
Yeah, there's 1 minute left. Is there any? Yeah, one last question.
Just coming back to dark matter. So, it's like, is it just like we know that it's there? Or is it like we at least know the location of the dark matter patches? Like, for example, what is the nearest patch of dark matter near Earth or something? And if it is, then is it something like invisible cloud? Even if we pass, we wouldn't know? Or it can collide at least? And
Yeah, so time's up. Thank you, Pedro, for a really interesting talk, and thank you for all the questions.